All right. Today we are continuing on. On Monday we introduced sampling distributions and as well as confidence intervals, and we'll expand on that, and then we will also introduce hypothesis tests, which is a very important kind of concept and framework that we will make use of. So I want to revisit this concept of a sampling distribution. And we said a sampling distribution is the distribution of possible sample statistics. And I said that, when you take a random sample from the population, because it's a random sample, some of the values, whenever you look at a summary statistic for that random sample, it's going to differ from one sample to another. And because of kind of, rules of probability and whatnot, some of those values, some of those sample statistics are going to be more likely than others. Okay, some of these values will have a higher probability than others. And so the sampling distribution is what is going to show us, it's going to show us the probability that a random sample produces a particular value of the sample statistic. So there's actually a little app on the internet that kind of illustrates some of this stuff here. Okay, so for illustration, all right. So the way this app works, let me kind of zoom in here a little bit. Okay, this is supposed to be kind of like I guess a candy machine or something. I don't know. Sometimes you go to, do they still have them at like the grocery store or the waiting section at the veterinary office or something? You put the quarter in, you twist the knob, and then a couple pieces of candy come out. So anyway, the idea here is, we've got some candy in here. These are Reese's Pieces. So they're like M&Ms, but they got peanut butter inside, and they only come in 3 colors: yellow, orange, and brown. Okay? And we're going to say, I'm going to draw 40 pieces, random pieces of candy out of this machine. I think that's what I said. Okay, yeah. Samples of size 40, we're going to choose 30% of the candies are orange. And we're going to just kind of draw a random sample. And when we draw the random sample, we're going to sort them. We're going to put the orange pieces on one side, and then the other colors, brown and yellow, on the other side. Okay? So just kind of by random chance, we do this. And in this sample, we drew 40 pieces of candy. We're expecting kind of 30% of them to be orange. Okay? And what we end up getting is we get 15. 15 divided by 40 is, what is that, 37.5% or something? Okay. 15 divided by 40, yeah. 37.5% or 0.375. And so we're going to put a little dot down here. Okay. Let me just kind of, here, let me turn off this show animation business here. So here's just another random sample. This sample, we got 13. 13 pieces are orange. 13 divided by 40 is 0.325. So I put a little dot here at 0.325. Okay. This one, only 7 pieces of candy were orange out of 40. Okay, out of 40, only 7 pieces. And so that's a proportion of 0.175. And so we put a dot here. And I can kind of repeat this over and over again. So here I got another sample with 13 pieces are orange. 32.5% orange. Here, 15 pieces orange, 37.5% orange. Okay, this one, how many is that? 18 pieces are orange. Okay, so that's 45% orange. Okay, here 11 pieces are orange, so that's 27.5%. Here's one, 35% orange, 42.5%. Here, this one, we get 30% orange, okay? And so every time I draw a random sample, sometimes we get a lot of orange, sometimes we get very few orange pieces, sometimes we get more or less. And every time I draw, I keep track of what proportion I get, what p hat I get, and I put a little dot down here in this dot plot. And I kind of just keep doing this over and over and over again, right? So here it is after doing 30 samples of 40. And to kind of speed things up, I can just say, let's do 10 samples, okay? So here we're going to add 10 dots to the plot here, okay? So here it is after 100 samples of size 40, there's 100 dots here. We can see, okay, samples of around 30% happen a lot, 32.5%, 27.5%. This shows up quite frequently. So let's just kind of accelerate this a little bit. So here it is after 300 samples. We've been keeping track of all of the different proportions that we've been getting, right? And again, we can see because the population is 30% orange, values around 30% show up most frequently. But again, because it's random, sometimes we get very few, like only 15% orange. Sometimes we get a lot, like 45, or it looks like 47.5% orange, okay? And at some point, the dots kind of stack up so much, and to get it to fit, the dots merge into a single straight line here, okay? So I'm going to go ahead and just keep going here, and our plot will get taller and taller. And effectively, what do we see? We see the sampling distribution begin to form. And this looks a lot like the normal distribution, and that's why we can approximate the sampling distribution with the normal distribution. Okay. Anyway, so this is this I thought was like just a neat little app or applet or web page that kind of illustrates, you know, if you wanted to generate a sampling distribution kind of via, you know, this kind of computer simulation here, right? So again, the idea, so this gives us kind of from random simulation, it gives us a sampling distribution and tells us exactly which samples are more likely to appear, and this is kind of based on actual simulated samples, right? So some of these samples ended up with proportions of 0.3, some of these samples ended up with proportions of, you know, 0.4, and you know, or I guess, I don't know, 4, something like that. Yeah, this sample had a proportion of 0.4, and we can actually see exactly which ones are more likely than others. And so here's just illustrating how this works, and each of these samples, I just did a couple of these things. So with 100 samples, you know, this is what we ended up doing, and with you know, way more, this is kind of the sampling distribution that I ended up with when I ran it and took some screenshots. Okay. And so based on so on Monday we said, you know, we can summarize our findings by saying this is the central limit theorem, and we said anytime you're looking at the sampling distribution of the proportion, the sampling distribution of p hat, then you are going to get something that looks like the normal distribution. And to define our normal distribution, we need to have a mean, and we need to have a standard error, standard deviation. The mean is the proportion p that exists in the population, and the standard error is the square root of p times 1 minus p divided by n. Okay, and then we said, okay, well, based on the sampling distribution and our understanding that the sampling distribution follows a normal distribution, based on that, we can create a confidence interval. And the central limit theorem tells us that whenever you take a random sample, the proportion of your sample, that proportion is going to be close to the population proportion. So if the population proportion is 30%, we expect our p hats, our random samples, to have proportions that are close to 30%. And we can kind of reverse this, and we can say, well, if we observe a sample proportion at a particular value, we can be confident that the population proportion is nearby. All right, so and specifically we said we can be about 95% confident that the population proportion is within 2 standard errors of p, or of p hat, that the population proportion p is within approximately 2 standard errors of p hat, and we created confidence intervals, and we did that on Monday. Right, and so this. I think the example we did was we said, I'm 95% confident that the proportion of Netflix, here we wrote subscribers, but probably just Netflix users, the proportion of Netflix users in the population is between 21 and 39%, okay? Now, I want to make an important distinction, and I want to say, it's important that we use this word confident. I'm 95% confident that the proportion is between 21 and 39%. And we don't want to say there's a 95% probability that the proportion is between 21 and 39%, okay? And that might be a little bit confusing to a lot of you, because this idea of being 95% confident kind of gives you the sense that, there's a 95% probability, or, we feel like there's a 95% chance that something's going to happen. I'm looking for a coin, but okay. Okay, so this is I don't have a coin, but all right. So I want to try to illustrate to you the difference between these two sentences. I'm 95% confident that the proportion of Netflix users is between 21 and 39%, and there's a 95% probability that the proportion of Netflix users is between 21 and 39%. Okay, so let me see. I think I'm going to go to this website where you flip a coin, right? And we'll just, okay, so I click the button and it comes out tails. Let's see, comes out heads. Okay, all right, so what I'm going to do, I'm going to tell you to close your eyes, and this includes those watching the video, okay? Close your eyes, I'm going to flip the coin, all right, and then I'm going to hide the web page, okay? All right, so open your eyes now. And I'm going to ask this question. Oh, you know what? I'm sorry. I messed up. Let me do this again. Okay. So this is what I'm going to do. All right. That's what I'm going to do. I'm going to flip the coin, and we're going to see whether it lands heads or tails. Okay. So, but sorry, I messed up. I need to ask you, before I flip the coin, what is the probability that the coin will land heads? It's not a trick question. It's 0.5. Okay, what's the probability that the coin will land heads? Okay, all right. Now I'm gonna go ahead and I'm gonna do it. And again, close your eyes. And I'm gonna push the button. Okay, so it flipped. Okay, and then go ahead and open your eyes. Okay, so now the question is, what is the probability that the coin landed heads? Okay, so you guys say 0.5, all right? And now, keep in mind, I did not actually close my eyes, so I actually saw how it landed. And maybe some of you didn't actually close your eyes. I don't know. So I'll ask again, what is the probability that the coin landed heads? I know how it landed, by the way. And now you're confused because what I'm asking. So the answer is, prior to flipping the coin, it made sense to ask, what is the probability that the coin will land heads? Okay, prior to flipping it, prior to me clicking that button, it made sense to ask the question, what is the probability that the coin will land heads? Because probabilities exist for uncertain events. However, once the coin was flipped, and once it landed, and once the answer appeared, it no longer makes sense to ask, what is the probability? Okay, what is the probability that the coin landed heads? Either it landed heads or it didn't land heads, okay? If you closed your eyes, you don't know how it landed, okay? If you closed your eyes, you don't know how it landed. So you would say, I'm 50% confident that it landed heads, okay? I'm 50% confident that it landed heads. But to say there's a 50% probability that it landed heads doesn't make sense. It either did land heads, and in this case it did, okay? Or it didn't land heads, all right? So either it did or it did not land heads. There's no sense in asking what is the probability, right? What is the probability that the image on the screen is tails? That's a nonsense question, okay? Or what's the probability that the image on the screen is heads? Okay, again, that's a nonsense question. There's no probability associated with something that has happened, okay? However, if you didn't see it happen, okay, if I said, all right, I flipped a coin and it's on this page, but you had your eyes closed, all you can say is I'm 50% confident that it landed heads, right? And so when we're talking about the proportion in the population, okay, the proportion of Netflix users in the population is some number. And that number is either inside my interval, okay, so maybe it's a number between 21 and 39%, like 24% or 38% or whatever. It's either within that interval or it's not, okay? It could be 40%, it could be 20%, it could be 18%. So either my interval is correct or it's not. It doesn't actually make sense to say there's a 95% probability that the interval is correct. Okay, either the interval actually got the real value within it or it didn't. Okay, we don't know how the answer, so we can only say I'm 95% confident that the population proportion P is between these two numbers. Okay, so that's kind of that's this idea of confidence, which is a little bit different from making a statement there's a 95% probability. Okay, in the textbook there's a section 7.5, and I'm going to skip it in the interest of trying to fit the content that I need to fit within our class time, because we don't have that much time. It's week 4, so we got week 5, and then so we have next week, and then Monday of week 6, and then we have the final exam. So not a ton of time left. So anyway, this is what we have. Okay, hypothesis tests. Let's introduce hypothesis tests. So statistical inference, again, the big picture in our course is that we want to make conclusions about the population based on samples of data, right? We observe a selection of kind of people or observations, and based on that, we want to make a conclusion about the big population that we did not observe directly, right? So we want to be able to make inferences from a small sample to the big population. And the confidence interval, which we introduced on Monday and talked a little bit more about today, that is one of the tools of statistical inference, okay? It allows us to look at a sample, and based on the proportion that we see in the sample, we're making a conclusion about the population. We're making a conclusion about the proportion of the population. Another tool of statistical inference is the hypothesis test, right? The hypothesis test is a framework, kind of this logical framework that we use that allows us to kind of make arguments or make conclusions about the population based on a sample, right? And so the hypothesis test is this framework, and in our class we're going to look at two types of hypothesis tests. We'll look at z-tests. I'll introduce that today, and then and next week we'll look at t-tests, which is for numeric variables and means and things like that. There are so many different kinds of hypothesis tests that exist and can be used, and they all use a very similar framework. The mechanics, the details of what happens in a hypothesis test changes from one type to another, but the same kind of logical framework exists in all of these things. As far as this intro class goes, again, we're only looking at those two types, the z-tests and the t-tests. But again, if you were to take more statistics in the future, or if you were to read, and pick up a, intermediate statistics textbook or something like that, or pick up even just a handbook on statistical tests, it'll have a listing of, maybe 50 different types of hypothesis tests that are out there for different kinds of data and different kinds of scenarios that you might encounter, okay? And the reason why we call it hypothesis testing is because what we do is we take any question that we have about the population. So you imagine any kind of question, and we turn that question into a testable hypothesis, we hear this word hypothesis, as part of like, what is the scientific method? And I don't know, maybe in elementary school, like in 2nd or 3rd grade or something, they introduced, what's the scientific method? And they say, you start off with a hypothesis, and then you gather data or evidence, and then you make your conclusion or something like that. I don't remember. And then you retest and things like that. And a lot of times, how would you describe what a hypothesis is? And sometimes they'll say a hypothesis is an educated guess. And I kind of personally don't like that definition of what a hypothesis is. Here I like to say, a hypothesis is going to be kind of a claim of what you're expecting to see. Okay, what you're expecting, or you're imagining a hypothetical situation. Okay, you're taking your hypothesis and you're going to imagine a hypothetical situation, and we are going to test this hypothesis, test this claim, by comparing what we would expect under this hypothetical situation versus what actually happened in reality. Okay. In order for the hypothesis to be testable, the hypothesis needs to be a very specific and exact claim. All right. So if your hypothesis is vague, there's no way for us to really test it. Okay. So if you wanted to make some kind of prediction that is, unverifiable, you just make it vague enough, and no one will be able to kind of verify or refute it, right? So, you could read some kind of, meet a fortune teller, and then, they'll say, I'm getting this reading that, someone, someone who used to be important to you and is no longer important to you, you'll have a conversation, they'll come back into your life, okay? And that's like so vague that it could apply to any situation, and there are so many situations that, you can't really test such a thing, okay? On the other hand, if the person makes a very specific claim and says, we're going to you're going to encounter, a person whose name, is, a person named Jacob on, the 25th of August, at this location. Okay, it's a very specific thing, and you can actually test to see if that actually happens or not, right? And so as far as something similar applies here, in that we can't just make vague claims, okay? We have to make a very specific claim, and we're going to test to see if that specific claim makes sense or not, okay? So for example, let's say, let's say there's a game of chance or something, okay? And in this case, playing somebody, you flip coins or something, and you're wondering, is this coin unfair? Okay, is the coin unfair? We want to test to see if someone is playing with an unfair coin that lands heads more often than tails, okay? So, you know, you flip a coin and if it lands heads or something, and we want to know, are they cheating in such a way that this coin lands heads more often than tails? Well, in order for us to make it a hypothesis that we can test, we can't just say, okay, we're using some kind of unfair coin. But the null hypothesis test the hypothesis that we're going to use is going to say that the coin has an exact property. And specifically, we are going to make the claim that the coin has a probability of landing heads is equal to exactly 0.5. That the probability that the coin lands heads is exactly 0.5. Or in other words, we're going to make the claim that the coin is fair. Okay? Claiming that the coin is fair is an exact property. Claiming that the coin is unfair is just vague. Okay? So in order to test it, we're going to say the coin is fair. All right? We pair it with an alternative that says the coin is unfair. But the test or the claim that we are going to test is the specific property that the coin is fair, which is that the probability it lands heads is equal to exactly 0.5, right? And maybe that seems a little counterintuitive because we're testing kind of the opposite claim that we want to see, right? But we, you know, stating that the coin is unfair can't be expressed as an exact property. So fair means P is equal to 0.5, and anything other than 0.5 is going to be unfair. And here we're going to say, we're going to test to see if P is equal to 0.5. And so one thing that will always be kind of helpful to remember is that when you set up your hypotheses, the hypothesis that you're going to test, which is what we call the null hypothesis, this one is always going to be equal, or always going to have an equal sign in it, right? It's going to be a specific thing that says the population parameter P or whatever it is exactly equal to some number. So here in this case, we're going to say that P is exactly equal to 0.5, and that's going to be the hypothesis that we test. Always has an equal sign. Okay. The null hypothesis is exact, and it gets paired with a kind of a inexact alternative. And so our alternative will be that if the coin isn't fair, then it must be unfair. And specifically, this coin has been kind of set up in such a way to give the player an advantage where they're flipping heads more often than 50%. All right, let me go ahead and give you your first view quiz answer for today. The first view quiz answer is the letter E. E as in elephant. E as in elephant. All right, so we have this null hypothesis, and we are going to test that null hypothesis against the data that we observe. All right, and so we start off, and the null hypothesis claims. So this is the logic of our hypothesis test. Okay, so the null hypothesis says the coin is fair, that the probability it lands heads is 0.5. This is kind of the claim, and we're going to just imagine what does life look like if the coin I'm playing with is fair. All right, and it's not that hard to imagine what life looks like if you have a fair coin, because probably most of the coins you've ever encountered were fair coins. All right. And we're going to take that kind of claim and imagine life in this hypothetical situation, and we're going to test it against our data. All right. So let's say we flip the coin a bunch of times, and our data says, hey, you know what? The coin landed heads 60% of the time. 60% of the time. That's higher. That's more than 50%. And so our question is, okay, if I'm imagining life in this hypothetical world where the coin is actually fair, all right, that this coin, whatever I have, let's just imagine that it is a fair coin. is the difference that I'm getting between 60% and 50%, is that actually significant, or could it be the result of randomness, right? Is it possible that my coin actually is fair, and just kind of by random chance, I ended up getting 60% heads, all right? Well, the answer to that question kind of depends on how many times we flipped the coin, right? Let's say I flipped the coin 10 times. If I flipped the coin 10 times and I got 6 heads, all right, instead of 5 heads, then my proportion of heads is 60% instead of 50%, right? But if I said, well, yeah, I flipped the coin 10 times and I got 6 heads out of 10, I don't think we would say, oh, the coin is unfair, right? We would say, yeah, that sounds pretty normal to me, okay? It seems completely reasonable that just by random chance, the coin landed heads 6 times out of 10 rather than 5 times out of 10, right? And so we could take that difference between 6 and 5, 60% and 50%, and we can just kind of explain that away with randomness. We can say, yeah, even if the coin were a fair coin, if you flip it 10 times, sure, we might expect it to be, we might anticipate getting 5 heads out of 10, but getting 6 heads out of 10 isn't that weird. Getting 4 heads out of 10 isn't that weird. Even getting 7 heads out of 10 isn't that unusual if you flip the coin 10 times, okay? On the other hand, if I had flipped the coin 1,000 times and I observed 600 heads versus 500 heads, right? So I flip the coin 1,000 times, I'm expecting something around 50% heads. I would expect something around 500 heads. Let's say I get 600 heads instead of 500, okay? I think we would say, oh, you know what? That seems a little strange. It doesn't seem like you just got lucky with the coin flips, okay? We would take that outcome and trying to claim that, oh, we just happen to get 600 heads and only 400 tails. I promise this coin is fair. We're not doing anything weird. That feels a little strange, right? It feels like, this kind of result shouldn't happen just by randomness. 600 heads out of 1,000 when we're expecting 500 heads, that seems a little bit strange. It seems like something fishy is going on. So in that case, we would say that, you know what? I don't think I got 600 heads just by randomness, that the difference between 60% and 50% does feel significant. Okay. Here I'm just kind of appealing to your intuition about probability, and I hope, I don't know, does that kind of make sense? That when we're looking only at 10 versus 1,000 head flips, our conclusions here would be different when we compare 60 to 50%, okay? So I mean, those are extreme cases, right? 1,000 versus 10. And at what point would we say the difference between 60% and 50% is significant, okay? Is it significant if I flip the coin 100 times and I get 60 versus 50? Is it significant if I flip it 200 times and I get 60% versus 50%? Is it significant if I flip it 80 times and I get 60% versus 50%? Okay, these are the kinds of questions that that we want to know, right? At 1,000, we say, oh yeah, okay, 60 versus 50%, that feels significant. But at what point do we say it is significant? So to answer this, we go through kind of a series of calculations to get something known as the p-value. So in a formal hypothesis test, we ask, what is the probability of getting our data or something more unusual if the null hypothesis were true? So we imagine what our data should look like if the null hypothesis were true. Okay, what do we expect to get if the null hypothesis were true? And we compare what we expected versus what we actually observed. And if there's kind of close alignment, we say, all right, checks out. Okay, on the other hand, if our data, what we actually observed, is very different from what we expected, that gives us that that indicates to us that our expectations were wrong, right? So if the reality is quite different from what you expected, we're going to say, yeah, your expectations, you had poor, your expectations were wrong, okay? And so anyway, the answer to this question, this probability question, what's the probability of observing our data or something more unusual if the null hypothesis were true? The answer to that is known as the p-value. The p-value is the probability of getting the data that we have or something more unusual if we assume that the null hypothesis were true. So, for example, let's revisit this example where we're flipping a coin, okay? We'll find the probability of getting a sample of flips where we get 60% heads or something more unusual if the coin were fair. So before we do any calculations, let's think about what could possibly happen, okay? One is that it ends up being very likely to get our data if the null hypothesis were true, or very unlikely. That means we get a small p-value. And then the other possibility is we do our calculations and we get a large p-value, that it turns out that it is not unlikely, all right? We have a high probability to get our data if the null hypothesis were true. So let's just kind of take a closer look at each of these things, right? So one possible outcome is that we do our calculations and it says it's very unlikely to get our data if the null hypothesis were true, right? So we talked about this example. We said, if our data is that we flipped the coin 1,000 times and we got 600 heads. So this actually, let's say this actually happens in our data, okay? We go through our calculations and our calculations say, maybe our calculations aren't even necessary. Our intuition will just say, hey, this kind of thing is really unlikely to happen if the coin were a fair coin, right? If it were a fair coin, and we could do this with the calculations, but it says, yeah, if we had a fair coin, the probability of getting 600 heads out of 1,000 flips is really, really, really low, okay? We're much more likely to get 500 or 501 heads out of 1,000 flips. Getting 600 heads out of 1,000 flips, the probability of getting that with a fair coin is very, very, very low, right? So we're saying if that null hypothesis were true, if we did have a fair coin, we shouldn't be getting this data. So the fact that we do have this data tells us what? The fact that we do actually have data where we got 600 heads out of 1,000 tells us that we are not in the situation where the coin is fair, okay? The reason why we got this isn't because the coin was fair and we had this miraculous, super lucky chance, super lucky outcome, but rather the coin isn't fair. The coin has a probability of landing heads of something different, and that's why I'm getting 600 heads. So maybe the probability of the coin lands heads is 58% or 62%, or maybe it's 60%. But that makes a lot more sense as far as why I'm getting this data, 600 heads out of 1,000, rather than to try to be stubborn and say, no, I have a fair coin, and we just happen to get, like a really lucky 1 in a million situation, right? Because technically it's not impossible, right? You could have a fair coin, and by some really weird, lucky circumstance, you get 600 heads out of 1,000. Okay, it's not impossible, but it's so incredibly unlikely that we conclude, you know what? I don't think I was the lucky one. I don't think I was the lucky one, right? I imagine, when someone performs a card trick, and they say pick a card, and you draw a card, and then they guess, and then later on they figure out what your card is. Okay. It's usually impressive, right? Usually, you draw a card and then they say, I'm going to read your mind. Oh, you're thinking of the Queen of Diamonds, okay? And it turns out to be correct. And usually, I think you would be impressed that they managed to get your card correct, okay? Now, technically, they had a 1 in 52 chance of just guessing correctly, okay? But if it happens, usually you want to just say, oh, you just got a lucky 1 in 52. You would probably say, oh, how'd you do that? How'd you know what my card was, okay? And the idea is that, the probability of it happening by random chance is pretty low, so we're not going to just assume that it was a lucky guess, but we're going to come to the conclusion that they did something. And we'd say, oh, how'd you do that, right? I want to know how you did that. How did you figure out my card? Because we have to suspect that they did something, that something happened that allowed them to figure out the card, and not that they were just randomly guessing, okay? And that's basically what we're saying here. The probability of this happening by random chance, while it's not 0, is low enough for us to say, I don't think it happened by random chance, that something else is going on. On the other hand, let's say it's not that unlikely to get our data if the null hypothesis were true, right? So we flip the coin 10 times, we end up getting 6 heads. And we ask, well, if you had a fair coin, is it, what's the probability of getting 6 heads out of 10? And it says, oh, you know what? Sure. When you flip the coin 10 times, you're expecting around 5 heads, but getting 6 heads isn't that weird in that there's a high probability, okay? Getting 60% heads or getting 6 heads out of 10 is not an unusual outcome. And because it's not unusual, the fact that it happens in our data doesn't really tell us much, okay? We can't conclude that the coin is unfair. We can't conclude that the coin is unfair, all right? At the same time, we can't make the conclusion and say, oh, well, the coin is definitely fair now, okay? So the coin landed heads 6 times out of 10, and the reason why it landed 6 times out of 10 could be that the coin actually is unfair and it lands 60% heads, okay? But it's just such a small sample that we're not going to make this conclusion, okay? A magic trick is not going to be impressive if there's a high probability of just guessing the answer correctly anyway, right? So if somebody says, hey, I'm going to do a magic trick, flip a coin, and it's going to land heads, and you flip the coin and it land heads, you're not going to be like, oh my gosh, how did you know? You'll just say, you'll probably say, do it again, okay? Because doing it once and guessing it correctly, it's not that impressive. Getting it correct, there was a 50% chance of getting it correct anyway, so it would not be that impressive. And so your natural instinct would just be like, oh, do it again, okay? Because we instinctively feel like, okay, if they can repeat it, then there's a lower probability of it happening, right? But if they refuse, they say, nope, it was a one-time deal, and they walk away, you'll be left with this nagging suspicion that, oh, maybe they just guessed and they got lucky, right? Versus they were actually figured something out as a way to predict the coin flip. All right, so that's kind of the logic. If the probability of getting our outcome, if the null hypothesis is low, then the fact that we have the data indicates to us that our null hypothesis is wrong. And on the other hand, if the probability of getting our data is not low, then that tells us that we don't have any reason to kind of throw out the null hypothesis or reject its claim. So before we go on, let me just cover a couple definitions here. We've been talking about the null hypothesis. And again, that's kind of the claim that the population has some exact property. The symbol we use for the null hypothesis is H0, like 0 for null, and H, I guess, for hypothesis. So H0 is our null hypothesis. This is the hypothesis that we test, and the null hypothesis always has an equal sign. The alternative is HA, and this is the alternative, and the alternative hypothesis is going to have either a greater than sign or a less than sign or a not equal sign. We go through some calculations to calculate our p-value, which is a probability, okay? And it's the probability of getting our data or something more unusual if we assume that the null hypothesis were true, okay? The p-value is a probability, so all the rules of probabilities apply. Specifically, or I guess importantly, probabilities are always numbers between 0 and 1. So if you ever do your calculations and you get a p-value that's greater than 1 or a p-value that's negative, you must have done something wrong, okay? And there's something known as the significance level. The symbol we use for that is alpha. And the significance level is just kind of an arbitrary value that we kind of draw in the sand, a line that we draw in the sand that decides whether or not we consider our p-value to be large or whether we consider our p-value to be small, okay? There are different kinds of hypothesis tests, and depending on how we write our alternative hypothesis will determine whether we have a one-sided test or a two-sided test, okay? One-sided tests have less than signs or greater than signs, okay? Whereas two-sided tests will have not equal signs. So the less than sign, when we have a less than sign in the alternative, remember the p-value is the probability of getting our data or something more unusual. And so with a less than sign in the alternative, more unusual means getting our sample statistic or something less than that, okay? So let's say we had a null hypothesis where we're expecting a proportion of 0.6 and our random sample ends up having a proportion of 40%. So we're expecting 60%, we only got 40%. In this case, more unusual means 40% or lower than that, okay? On the other hand, if our alternative has a greater than sign, then more unusual means something bigger than our sample's statistic. So if we're expecting 60%, for kind of the alternative, a greater than sign in the alternative to make sense, then our sample should have a proportion that's greater than 60%. So maybe we get a proportion of 80%. And now more unusual means 80% or something higher. More unusual means 80% or something higher. All right, let's, if you have a not equal sign, then more unusual is your sample statistic or farther away, okay, or farther away. So if you're expecting 60%, and let's say you observe your data, and your data has a proportion of 80%, okay? More unusual in this case would be 80% or higher, plus, well, 80% is 20 points more than 60, so we would go also in the opposite direction, and we would go down to 40%, 40% or less. So more unusual is, could we get 80% or higher? Could we also get 40% or lower? So more unusual is kind of like 20 points or farther away. 20 points or farther away. So that would be 80% or higher or 40% or lower if you're expecting 60%. So that'd be a two-sided alternative. Okay, this is kind of a lot of stuff. I think we'll look at some examples, and my hope is that it'll make a little bit more sense after we work through some examples here. All right, so let's try working through an example hypothesis test. Okay, so I think we've used this example before, and we want to know, is this carnival game a scam, right? So in the carnival game, there's this wheel, you spin it. The wheel is made to look like you have an equal chance of winning or losing, okay? There's 12 spaces, 6 of them are winner spaces, 6 are loser spaces, okay? And so we're expecting to win 50% of the time. We're expecting to win half the time. Okay, and our friend, he goes and he plays 25 games on the wheel. Okay, he plays 25 games, and he comes back and he says, I only won 8 times. I think the game is a scam. I think the game's a scam. I only won 8 times, and I played 25 times. So what do you think? Do you think the game's a scam? Or do you think our friend just got unlucky? Any guesses? We'll go through the calculations and we'll get it. But I don't know what your gut feeling is, right? So there's kind of, right? I mean, our friend does make a bit of a point. If the game is fair, we would expect him to win 12 and a half times. So, if he won 12 times out of 25, that would make sense. If he won 13 times out of 25, that would make sense. But he only won 8 times. 8 times seems like it's a lot less than 12 and a half. So now we have to wonder, okay, did our friend just get really unlucky? Okay, and how unlucky? Or is the game actually a scam, right? Did we get this result just by kind of random coincidence, or is this evidence that the game's a scam? So what we want to know is we want to do a hypothesis test. All right, so let me try this out here, okay? All right, so first we set up our hypotheses, okay? And our hypotheses are going to be that the null hypothesis is that the probability of winning, so we're going to say P is equal to the probability of winning, and our null hypothesis is that the game is fair, or alternatively, we can say P is equal to 0.5, that the probability of winning the game is 0.5. Our alternative is that the game is unfair, and specifically, probability of winning is less than 0.5. So we're going to say our alternative is that P is less than 0.5. So the fact that we have less than sign and the alternative means this is it is a one-sided test. Okay, so our null hypothesis is P is equal to 0.5. Our alternative is that the game is unfair. The probability of winning, these carnival game people, they've set up a scam so that winning the game is actually less than 0.5. Right? Okay. So what we're going to do is we are going to pick a confidence level, a significance level, and the kind of most common choice for significance level is 0.5. Okay? Now we could choose pretty much any value that we want, but we'll go ahead and use alpha of 0.05. This is our default significance level. Okay, so we have our default significance level of 5%, and this is going to be kind of our line in the sand that says, okay, if it's bigger than 5%, this is not unusual. If the probability is less than 5%, we'll consider it to be unusual. Okay, we'll also kind of check conditions to see if we can apply the central limit theorem. And so the conditions are, was our sample random and independent? All right, and so here we're going to say, yeah, you know what? If each game is independent, the outcome of one game doesn't affect the other. So it's independent, it's a random game of chance. So that condition's met. The large sample condition is that we need a sample size that's big enough. We need to have n times p greater than 10, and we need n times 1 minus p to be greater than 10. So n is 25, p is 0.5, n times p is 12.5, n times 1 minus p is also 12.5. Both of those numbers are bigger than 10, so our sample size is indeed big enough. Okay, and in our case, there's also the big population condition. This only applies if you're sampling from kind of a finite population, and here we're not sampling from a population. We're just we're doing repeated random trials. So this doesn't apply. We don't have to worry about that. All right, so we want to know what's the probability of observing our data or something more unusual if the null hypothesis were true. Okay, so what was our data here? So our data is that we played n equals 25, and we win only 8 times. So our p hat, okay, is going to be 8 divided by 25. Our p hat okay, we only won 32% of the time, right? I'm pretty sure that's correct. 8 over 25. Yeah, 32% of the time. So we only won 32% of the time. If the null hypothesis were true, okay, we expect to win, around 50% of the time. That didn't happen. We only won 32% of the time. So the question is, can we get 32% or less just by random chance, right? What is the probability of getting p hat less than or equal to 0.32, okay, if p were equal to 0.5, okay? So if the null hypothesis were true, we would expect a sampling distribution where the center is at 0.5, and we want to know, hey, you know what, I only got 32%. What's the probability I would get 32% just kind of by random chance? So let's assume that this is actually true, that p is actually equal to 0.5. What's the probability? What is p hat? Okay, what is the probability that p hat is less than or equal to 0.32? All right, so how do we do this? Okay, well, according to the central limit theorem, p hat comes from a normal distribution where the mean is going to be equal to 0.5, right? And our standard deviation, so the standard error, is the square root of p times 1 minus p over n. So if the null hypothesis were true, p is 0.5. 1 minus p is also going to be 0.5, and we're going to divide by 32. So this number, I'm sorry, 25. Thank you. All right, so what do I have here? I think 0.1, I don't know. 0.5 times 0.5 divided by 25, 0.01, and I'll take the square root of that. So I get a standard error of 0.1. All right, so that's convenient. Okay, and what is my z-score? So my z-score here is p hat minus kind of the p from my null hypothesis divided by the standard error. I get 0.32 minus 0.5 divided by 0.1. I get, so the numerator is negative 0.18 divided by 0.1 will give me negative 1.8. Okay, so my z-score is negative 1.8, and we want to know what is the probability we get negative 1.8 just kind of by random chance. Okay, so we go to our reference tables. So I think, here, let me just kind of go through this. So again, if the null hypothesis were true, we would expect our mean to be 0.5 and our standard error to be 0.5 times 1 minus 0.5 over 25, standard error 0.1. We go through our calculations, p hat minus p divided by the standard error, we get negative 1.8, and my reference tables, let's pull up the z table here. So we look up negative 1.80, and the probability of getting negative 1.80 or less is 0.0359. So this area the probability that so we get something a little under 4%. 4%. All right, so that's what we get. Okay, our p-value, the probability of getting, basically winning only 8 times out of 25, it could happen. You know, if you had bad luck, it could happen, and it's going to happen with a probability of around 3.5%. And so now the question is, do we think that's what happened to our friend? Okay, do we think our friend had bad luck and was just one of the unlucky 4% who will win only 8 times out of 25? Or is this enough for us to kind of be suspect of the game and say, you know what, I think something is wrong with the game, okay? So with a significance level of 5%. So remember, when we started off our test, we said, let's use the default significance level, 5%. And if we compare our p-value being 0.0359, our p-value is less than alpha. Okay, so we got around 3.5%, that's less than 5%. Our p-value is less than alpha, and so that indicates to us that our p-value is considered to be small. If we had assumed that the game were fair, it's pretty unlikely for you to play 25 games and only win 8 of them. Okay, we'd expect you to win more than 8. We'd expect you to win something closer to 12, but 9, 10, 11, something like that. Winning only 8 games out of 25 is pretty unusual. It happens only around 3.5% of the time. And so the fact that this thing happened, okay, we either can believe that we were just one of the unlucky 3%, or maybe the game is kind of rigged or set up in such a way that that it's unfair. Okay, so the fact that we did get this thing that is supposedly unusual kind of indicates to us that, yeah, you know what, maybe there's something going on in the game, and that's why I only won 8 times out of 25. Okay. Or we could give the game the benefit of the doubt and say, you know what, the game is fair, and I just happen to be really unlucky. Okay, so you can go either way. If your significance level is 5%, the conclusion you're going to be is, you know what, I think something's going on with the game. That's why I only won 8 times out of 25. Okay, so we conclude that the game isn't fair, but that the probability of winning actually is less than 0.5, and that's why we only won 32% of the time. Okay, now maybe if you were like I don't know, the gaming commission, and you have to enforce games to be fair, I don't know, maybe you wouldn't shut down the carnival game and say, you know what, there's some kind of cheating ring going on here. You probably would need more data. You'd need to collect more evidence to make your case. But as far as like, hey, should I ever play this game again? You'd probably say, you know what, I played it 25 times before. And I've come to the conclusion that it's unfair. I'm not going to play this game anymore, or something like that. Okay, so it could work that way. All right, questions on kind of the process that we've done so far. Okay, let me give you your second view quiz answer. Today's second view quiz answer is the letter B. B as in bear. B as in bear is your second view quiz answer. Okay, let's try out this example, and maybe I will. I'll let you guys try it out, and if you're watching the video, maybe pause the video and then just see if you can work through it. Okay, let me kind of give you an outline of what I want you to do. So for this one, all right, it says in the last census, we'll say Los Angeles County had a senior population that accounted for 20.2% of the population. So we'll say seniors are defined as age 62 or older, and we'll say 20.2% of Los Angeles County was age 62 or older. And so we want to know, okay, are the demographics of the county changing at all, right? So we'll say, set up hypotheses. Okay, set up your hypotheses. And so this will be 1. And then 2 will be, you can skip this. Normally you would check your conditions, but we'll just say skip it. All right, but step 3 will be calculate a p-value. And step 4 will be make your conclusion. All right, and just to kind of couple things, your z-score is calculated as p hat minus the p that shows up in your null hypothesis, which we call p0. You're going to divide by the standard error, and then the standard error is the square root of p, specifically the p that shows up in your null hypothesis, p0, times 1 minus p0 divided by n. All right, so why don't you take a few minutes and try this out. I'll go ahead and I'll pause the video here. If you're watching along, I recommend you pause and just try this out. Try this out. See if you can get your answers. Okay, let's go ahead and take a look at the answer. So if you're watching the video and if you haven't figured out the answer yet, you can pause again. But here we go. Okay, so our null hypothesis, whoops, here we go. The null hypothesis here is, remember the question was, do we have evidence, do the survey results provide evidence that the proportion of seniors in the county changed? So what we're saying is that in the last census, the proportion was 20.2%, okay? And so the null hypothesis will be the proportion is exactly the same as it was before. The proportion of seniors has not changed. That's going to be the null hypothesis in words. Symbolically, this means the proportion of seniors is still 0.202, okay? And then the alternative will be basically, as this question says, has the proportion of seniors changed? So changed does not imply that it got bigger or lower. It just means it's different, okay? So the proportion of seniors has changed will be the alternative here. So has changed just means no longer the same. So our alternative hypothesis symbolically that p is not equal to 0.202. Okay, so this time this is a two-sided test now. So anytime you have a not equal sign, it means you have a two-sided test. So that's going to be the hypotheses that you set up. All right, so we can check conditions. And I told you to skip this, but we got independent random. And then we have sample large enough, sample size is large, and population big. So are these conditions met? Okay, here it says 150 randomly selected people. So that indicates to us that that condition is met. Is the sample size large? We need to check n times p is greater than 10, and n times 1 minus p is greater than or equal to 10. Okay, or in our case, because we just have counts, we need at least 36 yeses and at least 10 yeses or 10 nos. So greater than or equal to 10 yes, greater than or equal to 10 no. All right, so we have 36 yes seniors, and with 150 total, that means 150 minus 36, 114 no. Okay, both are greater than or equal to 10. So that condition is met. Population big. Population is Los Angeles County. Population is big. Los Angeles County has like 4 million people. Condition met. Okay, you just want to make sure you're not sampling over 10%. So as long as our county had more than 1,500 people, we're not sampling over 10%. So we're not worried. All right, so let's go ahead and do our p-value calculations. So if the null hypothesis were true, then we expect our p hat to come from a normal distribution where the mean is going to equal to 0.202. That's the value in our null hypothesis. And then the standard error is going to be, well, the standard error is the square root of p0 times 1 minus p0 over n, 0.202 times 0.798 divided by, we have 150 people. So what is this? Where's my calculator? Okay. 0.202 times 0.798 divided by 150. And what's the square root of this? 0.03278. That's my standard error. Okay, so here's my little picture. Whoops. If the null hypothesis were true, we're expecting to be at 0.202. Oh, actually, we never bothered to calculate our p-hat. Our p-hat is how many seniors do we get divided by our sample size. We counted 36 seniors in a sample size of 150. So what's that? 36 divided by 150, 24%. So in our sample, we have 0.24. So we want to know what's the probability that by randomness, I wrote 0.25, that we would get 24% or something greater. And also, because of the not equal sign, we want to go to the other side. And, well, 24% is like, what is that, 4% more? A little bit, 3.8%. I don't know what this is. Okay, 24 minus 0.202 is 0.038. So what's 0.202 minus 0.038? That would take us to 16.4%, right? 0.164. So 0.164 or less. But really, we can just find the area to the, we can just find this area and multiply it by 2. So what is the probability of, oh no, what is the probability of being at 0.24 or that p hat is greater than 0.24 or p hat is less than 0.164, okay? And we can just say this is going to be equal to 2 times the probability that p hat is greater than 0.24, yeah? Greater than or equal to, I guess. Okay, so we will get our z-score. Z-score is p hat minus the p from our null hypothesis divided by our standard error. We observe 24%. We will subtract off the mean, 0.202, divide by our standard error of 0.03278. Okay, so so the difference is 0.038. 24 minus 0.202 is 0.038. We're going to divide that by 0.03278. I get a z-score of 1.16. Okay, so the area to the right of z equal to 1.16 is equal to, so I go to my z table, I'm going to look up 1.16, and I get 0.1230. 1.16, you know, 1 minus that is 0.1230. So this is going to be 0.1230 on this side. And over here, we're going to have 0.1230 as well, because it's symmetric. So my total p-value here is 0.1230 times 2, 0.2460, okay? 0.2460. So around 25%. So what we're saying is that even if the proportion of seniors didn't change, okay, so our sample was 24%, right? 24% seniors. All right, okay, the census last time is 20.2% seniors, right? And what we're saying is that even if the proportion of seniors is exactly the same, just by random chance, we could get a sample where it's 24% seniors. 0.24. Okay, this happens with probability 0.246. Uh, 2460, which is not unusual, and therefore we will not reject the null hypothesis. The p-value, this is the tail area. This is one tail probability. And it's double that because we have a two-sided test. So this is one tail area is 0.1230. And then the p-value is double that, 0.246. And yeah, it's greater than 5%. So that's kind of our threshold. We say anytime you get a p-value greater than 5%, we're gonna, we'll say our probability is large, and we're not gonna reject the null hypothesis. Exactly. Okay, so I think these are all of the steps here. Okay, so 0.202, 0.0328, I kept another decimal point, 0.03278. And test statistic of 1.16. We look this up in the table. We'll get 2 times 0.1230. Get 2.246. And our conclusion is this. So our sample is 24% seniors, which is higher than 20.2%. And our p-value is 0.246. So even if the county's senior population were still 20.2%, okay, we could, just by random chance, end up getting a sample of 150 seniors where we end up getting 24% seniors. Okay, 150 people where we get 24% seniors, or something more unusual. So this is considered a high probability, and so even though 24% is different from the expected proportion of 20%, 20.2%, it's not considered to be that unusual. And so we would say our survey does not provide enough evidence to say that the proportion of seniors has changed. Okay? Now, it doesn't necessarily mean that the proportion of seniors has stayed exactly the same at 20.2%. It's just we don't have enough data. Having only 150 people is not enough data for us to kind of conclusively make a statement that says the proportion of seniors has changed, that the demographics are changing. All we can say is, yeah, you know what? In our sample, it's a little bit higher, but our sample wasn't big enough for us to kind of make a conclusive statement here. All right, how do we feel about this? Kind of the setup and the logic of this. All right, so this is going to be important. We'll cover a little bit more of some of the conceptual ideas that go into a hypothesis test. We'll take a look at that on Monday, but this will be kind of the introduction to hypothesis testing and statistical inference, and next week we'll kind of get a little bit more deeper and look at t-tests, the other kind of hypothesis tests that we'll explore. But that will be it for today. We'll wrap it up here. Let me give you your last view quiz answer. Last view quiz answer is the letter B. B as in bear is your last view quiz answer. So we'll go ahead and end here. Have a good rest of your day. Good luck with everything, and we'll see you on Monday.